welcome to the next session in the Cyber Defenders program. In this session, we're going to take a look at network security. And to avoid getting bogged down in details in such a short lecture, we're actually going to take a pretty high-level bird's-eye view by using an example to introduce network security. Network security is a pretty broad term. Most any device or piece of software these days connects to the internet, and so network security is essentially morphed into meaning computer security. There are several hierarchical levels in the internet that work together so that information flows to and from, but each component has its own set of unique vulnerabilities. And we'll keep that in mind as we look at various examples in this lecture. The best way to understand network security is actually to just look at how information flows to and from devices and what components are used in the middle to move it around. So you might be familiar with this meme from the Super Bowl where a young kid, probably 10 years old, is partying with Justin Timberlake in the stands, but probably doesn't know who Justin Timberlake is because he's too young. And it looks like he Googled searched Justin Timberlake right before taking a selfie with him. That's the meme. Whether it's true or not, who cares? So what actually happens when you type "who is Justin Timberlake" in your browser? This is a typical networking and security interview question. And it seems pretty simple, but you could actually go really deep into what happens networking-wise, computing-wise, so on and so forth. And so in an interview, you could see this question taking 30 minutes, an hour. I've seen it take that long. But for this example, we'll take a condensed explanation, hopefully something around 10 minutes. So here's another meme. It's the new phone who dis meme, which is kind of a good introduction of how DNS works on the internet. When Delonte is trying to reach Trey, but doesn't have Trey in his contacts app anymore, he defaults to using his number, something that he's not very familiar with. And that's why he ends up going to the wrong person. He needs something to help him translate names to numbers. And just like we do that with the contacts app on our phone, the internet kind of does that too. When you type in something that you're familiar with, www.google.com, that actually translates to an IP, a number. And the internet uses IPs to identify devices and hosts across the internet and communicate between them. So as I alluded to earlier, DNS, the domain name service, is essentially the contacts app for the entire internet. It's a central service that translates names, like we saw google.com, into IP addresses, which are numbers. IP addresses these days might look like 108.177.98.106, or it might be letters and numbers separated by colons. And that's because there's a newer version called IPv6. Don't get too bogged down in the details of that right now. We might revisit that at the end of the lecture. So DNS, when your device initially connects to like a Wi-Fi router or your cellular phone network, it needs to know who to ask to make these translations between domain names and numbers. Usually these DNS settings are actually pushed to your device right when it connects, so it knows who to ask the IP address for google.com. Likewise, Google will claim ownership of the domain www.google.com and register the domain name with a special registrar so that everybody knows the IP address for google.com. DNS has quite a few levels. In fact, while there are a few root servers that handle the core truth for all DNS entries, we rarely ask these DNS servers when we have a question for an IP address. Instead, all the levels in between your query and the actual root servers save the answers along the way, known as a cache. This way we can save time and be more efficient. So for example, if you were to ask the IP address for google.com from your browser will check its own cache if it has one for whether it's searched for google.com before, searched for google.com's IP address before. You might search your operating system's cache as well. Then you might search your home router, it has a cache, or your company router if you're at work. Then the internet provider for your home or company, that might also have a DNS server. And it can eventually go back to the root servers, but it rarely does because most people around you are also asking for the IP address for Google as well, and for many other sites. So, can you think of any potential security issues here with DNS? We mentioned it has this cache, and we rely on that cache for answers at each level. What if you accidentally typed in www.google.com? A little typo. We've all done this before. Sometimes google.com will host that website and redirect you to the right website. Other times, a typo like that will take you to a weird advertising website or something like that. It's kind of called typo squatting. It's an attack usually used for advertising purposes, but it can also be used for malware or delivering incorrect information to somebody. So if somebody impersonates google.com when you type in www.google.com, they could recreate the google.com homepage, ask you to log in, steal your username and password. They could host advertisements and make money that way. So that's kind of a big problem. What else? What if one of the caches along the way for the DNS query, say at your Wi-Fi router, or at the DNS server at your ISP, what if that cache is compromised, and instead of telling you to go to the actual IP address for google.com, it tells you to go to some other IP address? That other IP address could be any website that the attacker can host their own content on. And likewise, in the previous example, it could impersonate Google, it could deliver advertising, deliver malware to your computer. This one's known as DNS cache poisoning. Another one. What happens if someone changes the ownership registration for the domain google.com? Google.com is the owner, but every year or so, the registration for that domain is renewed. If google.com misses it or somebody else hacks into it and changes the registration, they could have the domain point to somebody else, somewhere else. This is called registrar hijacking. Very unlikely for Google to succumb to that, but smaller websites can have that issue. Assuming we've passed all those hurdles of security issues, we should have an IP address for google.com. Now that we have that IP address, what are we going to do to communicate with google.com? After all, we asked it a question. So before we ask the question, we have to figure out a way to communicate with google.com. Just like you can choose to talk to your friend over text message, iMessage, Google Hangouts, Snapchat, Instagram, whatever, the computer that you're on needs to figure out a way to talk to Google's server. And typically from the browser, they use a communication method called TCP, or Transmission Control Protocol. The reason that's used is it's a relatively reliable way to send data back and forth the wide internet, even if the connection is a little spotty or something can happen to drop data over that long route. So that connection setup is going to go from your device over a cell phone network or a Wi-Fi, over Wi-Fi to a router, then to your internet provider, and then across many hops to finally get to a Google server, and then they're going to return saying that they acknowledge that communication setup, and it's kind of a handshake for TCP that sets that up. So now that we have our connection set up, we're now finally able to send the actual question to Google's server, who is Justin Timberlake. And it's going to use a higher level protocol, something you're probably familiar with, HTTP. After all, we type that into our browsers often. And it's going to send a post request with our question to Google. So if you were ever to use Google's developer tools, which is just pretty easy to get to in the options toolbar, you'll see the other tab right here, hopefully you can see that, where you can see request and response headers from your machine going to Google and response headers from Google coming back to you. And you'll see a few interesting things. You'll see the request URL. You'll see that we had a method post because we're asking some questions. Essentially, we're posting some data along with our request. If we just asked for the Google homepage without asking a question, it would have been a HTTP GET instead of an HTTP POST because there would be no data that we're providing in that scenario. But here we're asking a question, so it's going to be a POST. You'll notice some other interesting things. We had a status code returned to us saying that essentially that the request was received and it was okay, and we're sending you some content back. The request headers that we sent to them has something called a cookie, which we'll get into in a second. You can see some other interesting things, like the user agent is a description of the web browser and machine that is asking the question. So in my machine, it's Windows 10, It's using a Chrome browser, which uses the same rendering engine as quite a few other browsers, but we'll go ahead and go to the next step here. So we sent out one post request to google.com, and what you'll see in that previous slide that I just showed is that google.com sent several HTTP responses. Why is that? Well, the web page for the Google search results is composed of not just text, not just images, but also instructions to ask for more content. Maybe that's like personalized content for the account information in the upper right for your account settings, etc., etc. So a single HTTP request from your device will often result in several responses and more requests and more responses. And just like we did with TCP, these go the entire route across the internet. They're going to go from your device over Wi-Fi to a router, to your internet service provider, and then back to you from Google server. And you'll notice that some of the results, some of the text, and the account settings will be customized, right? Because Google knows your account, you've visited before, and this is usually done by Google leaving what's known as a cookie or a little breadcrumb that says, hey, I've been here before at Google. And so Google says, okay, let me track that so that I can give you personalized content. And that cookie is tied to Google. And the next time you visit, your browser will say, hey, I have this cookie for Google. Give me personalized content based on that. So what could go wrong with some of these HTTP responses and requests? Well, we just mentioned cookies. What if google.com's cookie on your computer was compromised, like a bad website or a program tricked you into giving it up? Well, now somebody can actually impersonate your browser session with google.com and kind of maybe log in a Gmail on your behalf, go into Google Wallet, something bad like that. And this is known as session forgery or cross-site scripting. Here's another one. What if something in the network between you and Google, like that Wi-Fi router we mentioned, a server along the way, maybe a core internet router, was used to either fake your request or fake Google's responses? After all, once you give up the question and send it along its way, you don't really have any insight as to who's touching your data as it moves all the way across the internet to Google's server. This is known as a man-in-the-middle attack, and the reason this happens is people can impersonate and kind of replay the request, the response, and modify data in between. So let's say you thought you were talking to your bank, they were showing your balances, and it shows that you had an $800 balance, but a crook who can play a man-in-the-middle attack can actually rewrite the web page on the fly to show that you had an $800 balance, even if you just cashed out the last $800 in your account. So it can be a pretty dangerous thing if somehow somebody's able to compromise content in between you and Google. So this is what might happen in a man-in-the-middle attack. If you asked who is Justin Timberlake, and you got results back for Justin Bieber, it looks like somebody kind of altered the content on the way back. This might sound kind of far-fetched, but this does happen. Actually, the NSA was found to be, for very high-value targets, I would assume, taking routers that were shipped to companies, and while they were being shipped out, like by UPS or DHL, they would actually intercept the shipment, open up the package, write some custom firmware or custom software on the device, package up the package with the new seal, and ship it on its way. And they wouldn't know, the receiving end wouldn't know that the thing has been tampered with. And maybe the thing is changing the results, maybe it's siphoning off data somewhere else. So this does happen in the wild. That's an extreme example, but there's less extreme examples, like the two-factor authentication you might be familiar with, where you get a code for SMS. That's been known to be susceptible to man-in-the-middle attacks. So these do happen, and when they do happen, it's really scary because the user doesn't actually know that that's happening. So as we kind of wind down, keep in mind the attacker mentality. Always kind of challenge a network assumption. Any level of the networking stack, any component in the network can be compromised. But usually the attacker is trying to find the right balance of how easy it is, right, to make the attack, and easy is in terms of their time, their money, and then how anonymous can they remain while attacking? And then what kind of power can they gain from attacking it? Can they gain information that's valuable? Can they gain money? And so if you were to think of email spam, an attacker has to do very little work to send millions or billions of emails out. They could get a 0.0001% hit rate of somebody clicking it and choosing to buy the Viagra pills or download the program, whatever it is they're trying to do. But even at that low rate, at that scale, it might be quite a few hundred or thousands of people who do this, and they can make a lot of money. On the flip side, I gave that NSA example. Very expensive, a lot of money to do that attack. They can remain pretty anonymous while doing it, and they might be able to get some, very specialized information from that. So for them, that was the right balance as an attacker to do it. So it's always finding the balance, right? The spam attacker in a foreign country, or even in the U.S., I should say, may not do what the NSA did because they don't have those types of resources. And so we'll kind of leave off as we go into the lab exercise talking about Wi-Fi. Keep in mind, Wi-Fi is extremely easy to use. It's also extremely easy to attack, and that's because Wi-Fi signals by design have great coverage, at least in a small few hundred feet radius, and they're designed to commute with any device. Any device is supposed to be able to connect to Wi-Fi, and so it's pretty easy to kind of observe Wi-Fi signals around you, and then you can use that to kind of observe or gain some insights as the information being sent on the devices around you, and if you're an attacker, impersonate or steal that information. So that's the end of the lecture, and the next section for this will be actually a lab exercise. So stay tuned for that, and thanks for listening to this session on network security. Thank you.